Hello everyone, my name is Dittawat Taichaiyaphum. This video will explain you the contents of the transmission line in each chapter in the midterm, which consists of network theorem, resonance, two-port network, and filter. And the first topic that we talk about is a network theorem. And the first one theorem that should explain is a superposition theorem. The superposition theorem is used to solve complex network with a number of energy sources. It is an important concept to determine the voltage and current across the element by calculating the effect of each source individually and combine the effect of all sources to get the actual voltage and current of the circuit element. Explanation of superposition theorem. To let us understand the superposition theorem with the help of an example, the circuit diagram is shown in this consists of two voltage sources V1 and V2. First, take the source V1 alone and short circuit the V2 source as shown in the figure of the circuit diagram. Here, the value of the current flowing in each branch I1, I2, I3 is calculated by the following equation. The difference between above two equations gives the value of the current I3. Now activating the voltage source V2 and deactivating the voltage source V1 by short circuit it and we will find the various current of I1, I2, I3. Here and we got the value of the current I3 will be calculated by the equation shown in this figure. As per the superposition theorem, the value of current I1, I2, I3 is now calculated as in this figure. The direction of the current should be taken care of while finding the current in the various branches. In the next theorem is about reciprocity theorem. Reciprocity theorem is a state that in any branch of a network of circuit, the current due to a single source of the voltage in the network is equal to the current through that branch in which the source was ordinarily placed when the source is again put in the branch in which the current was originally obtained. This theorem is used in the bilateral linear network which consists of bilateral components. The location of the voltage source and the current source may be interchanged without a change in current. However, the polarity of the voltage source should be identical with the direction of the branch current in each position. The reciprocity theorem is explained with the help of the circuit diagram shown in the figure. The various resistance R1, R2, and R3 is connected in the circuit diagram with a voltage source and current source. It is clear from the figure above that the voltage source and the current source are interchanged for solving the network with the help of reciprocity theorem. And the next theorem is about Thevenin theorem. The Thevenin theorem is the state that any complicated network across its load terminal can be substituted by a voltage source with a one resistance in series. This theorem helps in the study of the variation of current in a particular branch when the resistance of the branch is varied while the remaining network remains the same. Explanation of Thevenin theorem. The Thevenin statement is explained with the help of a circuit in the figure. Let us consider a simple DC circuit as shown in the figure, where we find the load current IL by the Thevenin theorem. In order to find the equivalent voltage source, IL is removed from the circuit as shown in the figure, and VOC or VTH is calculated. So we got the equation on this figure. Now to find the internal resistance of the network in series with the open circuit voltage, VOC also known as Thevenin voltage. VTH, the voltage source is removed, or we can say it deactivated by a short circuit, as the source does not have any internal resistance as shown in the figure. Therefore, we got this equation, and so as per Thevenin statement, the load current is determined by the circuit shown in the above. The equivalent the Thevenin circuit is obtained. The load current IL is given us as in this equation. IL equal VTH over RTH plus RL, where the VTH is the Thevenin equivalent voltage. It is an open circuit voltage across the terminal AB known as load terminal. And the RTH is the Thevenin equivalent resistance as seen from the load terminal, where all the sources are replaced by their internal impedance, and the RL is the load resistance. And the next theorem is a Norton theorem. Norton theorem is stated that a linear active network consisting of the independent or dependent voltage source and current source and the various circuit elements can be substituted by an equivalent circuit consisting of a current source in parallel with a resistance, the current source being the short circuit current across the load terminal and the resistance being the internal resistance of the source network. Explanation of Norton theorem. To understand Norton theorem in detail, let us consider a circuit diagram in the figure. In order to find the current through the load resistance IL as shown in the figure, the load resistance had to be short circuit as shown in the diagram in the next one. Now the value of current I flowing in the circuit is found out by the equation of this equation. And the short circuit current ISC is given by the equation on this one. Now the short circuit is removed and the independent source is deactivated as shown in the circuit diagram, and the value of the interval resistance is calculated by this equation. R int equal R2 plus R1 multiplied by R3 over R1 plus R3. And as per Norton theorem, the equivalent source circuit would contain a current source in parallel to the internal resistance, the current source being the short circuit current across the short terminal of the load resistor. The Norton equivalent is represented as this one in this figure. And finally, the load current IL calculated by this equation, where the IL is the load current, ISC is the short circuit current, RINT is the internal resistance of the circuit, and the RL is the load resistance of the circuit. In the next one is a Neumann theorem. The Neumann theorem is stated that when a number of voltage sources V1, V2, V3, or Vn are in parallel having internal resistance R1, R2, R3 to Rn, respectively, the arrangement can be replaced by a single equivalent voltage source V in series with an equivalent series resistance R. In other words, it determines the voltage across the parallel branch of the circuit which have more than one voltage source. Explanation of Neumann theorem. Assuming a DC network on numerous parallel voltage source with internal resistance supplying power to load resistance RL as shown in the figure, let I represent the resultant current of the parallel current source, while G is the equivalent conductance as shown in the figure, and you will see the next resulting current source is converted to an equivalent voltage source as shown in the figure, and we got this equation. The positive and negative side appear to include the case where the source may not be supplying current in the same direction, and also in this equation we as known as I equal V over R, and we can also write R equal I over G as G equal I over R. So the equation can be written on this figure, where the R is the equivalent resistance connected to the equivalent voltage source in series. Thus, the final equation will become this equation. In the next theorem is a maximum power transfer. State that a resistive load being connected to a DC network receives maximum power when the load resistance is equal to the internal resistance as known as Thevenin equivalent resistance of the source network as seen from the load terminal. The maximum power transfer theorem is used to find the load resistance for which there would be the maximum amount of power transfer from the source to the load. Explanation of maximum power transfer. A variable resistance IL is connected to a DC source network as shown in the figure, and the figure B represents the Thevenin voltage VTH and Thevenin resistance RTH of the source network. The concept of maximum power transfer theorem is that by making the source resistance equal to the load resistance, which has wide application in communication circuit where the magnitude of the power transfer to sufficiently small to achieve maximum power transfer, the source and the load resistance are matched, and with this efficiency become 50% with the flow of maximum power from the source to the load. And in the electrical power transmission system, the load resistance being sufficiently greater than the source resistance, it is difficult to achieve the condition of the maximum power transfer. And the next theorem is a substitution theorem. Substitution theorem states that a voltage across any branch of the current to that branch of a network being known, the branch can be replaced by the combination of various elements that will make the same voltage and current through that branch. In other words, the substitution theorem says that for a branch equivalent, the terminal voltage and current must be the same. And the explanation of substitution theorem simply, one can say that the substitution theorem is the replacement of the one element with another equivalent element. In a network, if any element is substituted or replaced by a voltage or current source, whose voltage or current across or through that element will remain unchanged at the previous network. To let us understand the theorem with the help of the circuit diagram below. Here, various resistance R1, R2, R3 is connected across the voltage source. The current I is flowing through the circuit, which is dividing the current I1 flowing through the resistance R1, and the current I2 flowing through the resistance R2, V2, V1, and V3. Are the voltage drop across the resistance R1, R2, and R3 respectively. Now, if the resistance R3 is substituted by the voltage source V3 as shown in the figure, in the circuit diagram as shown in the figure, R3 is replaced by the current flowing through that element, I1. In both the cases shown above, if the element is substituted by the voltage source or the current source, when also the initial condition of the circuit does not alter. And this means the voltage across the resistance and current flowing through the resistance unaltered, even if they are substituted by the other source. Compensation theorem. Compensation theorem states that in a linear time invariant network, when the resistance of an uncoupled branch carrying a current is changed by the delta R, then the current is on the branch whose change and can be obtained by assuming that an ideal voltage source of Vc has been connected such that Vc equal I delta R in series with R plus delta R when all other sources in the network are replaced by their internal resistance. Explanation of the compensation theorem. Let us assume a load RL be connected to a DC source network whose the Thevenin equivalent keep V0 as the Thevenin voltage and RTH at a Thevenin resistance as shown in the figure. And here we got the equation. Let the load resistance RL be changed to RL plus delta RL. Since the rest of the circuit remain unchanged, the Thevenin equivalent network remain the same as shown in the circuit in the figure. Here we got this equation, and the change of current being termed as delta I. Therefore, delta I is equal in this equation. And then we putting the value of I dat and I from the equation 1 and 2 in the equation 3, we will get this equation. Now putting the value of phi from the equation 1 in equation 4, we will get the following equation on this figure. So as we know, Vc is equal I delta IL, and it is known as compensating voltage. Therefore, equation phi is become in this figure. Hence, the compensation theorem tells that with the change of branch resistor, branch current change, and the change is equivalent to an ideal compensating voltage source in series with the branch opposing the original current, where all other sources in the network being replaced by their internal resistance. And the last theorem that we talk about is Taichaiyaphum theorem. Taichaiyaphum theorem is stated that the summation of power delivered is zero for each branch of any electrical circuit at any instant of the time. It is mainly applicable for designing the filter in the signal processing. Explanation of Taichaiyaphum theorem. Taichaiyaphum theorem can be also stated in another word as in any linear, nonlinear, passive, active, time variant or time invariant network to the summation of power. Thus, for the K powered by Th branch, this theorem states that in this equation, where the n is the number of branches and the Vk is the voltage in the branch, Ik is the current flowing through the branch. Let this equation show the Kth branch through the current. Vk is the voltage drop in branch K and is given as this equation, and where the Vp and Vq are the respectively node voltage at P and Q node. And this we have this equation. For the summing the above of these two equations, we will get this equation. Such equation can be written for every one of the network assuming in branch. The equation will be this equation in the figure. And however, according to the Kirchhoff's current law, the algebraic sum of current at each node is equal to 0. Therefore, this equation will obtained by this equation. And the next topic that we talk about is about resonance. In physics, resonance is the tendency of a system to oscillate with larger amplitude at some frequency than the other. These are known as the system resonance frequency. At this frequency, every small periodic driving force can produce large amplitude oscillation. Resonance occurs when a system is able to store easily transfer energy between two or more different storage modes. And however, there are some losses of cycle to cycle, called damping. When damping is small, the resonance frequency is approximately equal to the natural frequency of the system, which is a frequency of unforced vibration. Some systems have multiple distinct resonance frequencies. In the first topic about resonance is CD RLC resonance circuit. In an RLC circuit, the resonance is the state at which the reactance of the inductor XL and the reactance of the capacitor is XC are equal. It is used in various applications including filter, oscillator, frequency meter, and tune amplifier. And consider a RLC circuit in which resistor, inductor, and capacitor are connected in series across the voltage supply. This series RLC circuit has a distinguishing property of resonating at a specific frequency called resonance frequency. In this circuit containing inductor and capacitor, the energy is stored in two different ways. When a current flows in an inductor, energy gets stored in the magnetic field. So when the capacitor is charged, energy gets stored in the static electric field. Variation in inductive reactance and capacitive reactance with frequency. On this figure, we will know the inductive reactance is XL equal to 2 pi multiplied by FL. Mean inductive reactance is directly proportional to frequency. When the frequency is 0, or in case of DC, inductive reactance is also 0. The circuit acts as a short circuit, but when frequency increases, inductive reactance also increases. At the infinite frequency, inductive reactance becomes infinity and circuit behaves as open circuit. The next one is about variation of capacitive reactance. with frequency. In this figure, it is clear from the formula of capacitive reactance Xc equal 1 over 2 pi Fc that frequency and capacitive reactance are inversely proportional to each other. In case of DC or when frequency is zero, capacitive reactance become infinity, and circuit behave as open circuit. And when frequency increase and become infinity, capacitive reactance decrease and become zero at infinity frequency. At that point, the circuit acts as a short circuit, so the capacitive reactance increase when decrease in frequency. If we plot a graph between capacitive reactance and frequency is an hyperbolic curve as shown in the figure. Resonance current. In this figure, in series RLC circuit, the total voltage is phasor sum of voltage across resistor, inductor, and capacitor. At the resonance in series RLC circuit, both inductive and capacitive reactance cancel each other, and we know that the series circuit, the current flowing through all the elements is same, so the voltage across the inductor and capacitor is equal in magnitude and opposite in direction, and thereby they cancel each other. So in a series resonance circuit, voltage across resistor is equal to supply voltage, V equal VR. In series RLC circuit, current is I equal V over C, but at resonance current I equal V over R. Therefore, the current at resonance frequency is maximum as at the resonance in an impedance of circuit is resistant only and is minimum. The above graph show the plot between circuit current and frequency. As starting when the frequency increase, the impedance CC decrease and hence the circuit current is increased. Power factor at resonance. In this figure, at resonance, the inductive reactance is equal to capacitive reactance, and hence the voltage across inductor and capacitor cancel each other. The total impedance of circuit is resistant only, so the circuit behave like a pure resistive circuit, and we know that in pure resistive circuit, voltage and the circuit current are in the same phase. V1, V, and I are in the same phase direction, therefore the phase angle between voltage and current is zero, and the power factor is unity. Summary of the series RLC resonance circuit. For series RLC circuit at certain frequency called resonance frequency, the following point must be remembered. So at resonance, first, inductive reactance L is equal to the capacitive reactance Xc. Second, total impedance of circuit become minimum, which is equal to R. So the third one is circuit current become maximum as impedance reduce, I equal V over R. So the next one is the voltage across the inductor and capacitor cancel each other, so voltage across the resistor VR equal V supply voltage. And the number 5, since net reactance is zero, circuit become purely resistive circuit, and hence the voltage and the current are in the same phase, so the phase angle between them is zero. In the next one is the power factor is unity. And the last lesson that we got from this is a frequency at which resonance in series RLC is occur, given by this equation. Parallel RLC resonance circuit, or we can call anti-resonance circuit. A parallel RLC resonance circuit is shown in the figure. The input impedance is given by this equation. At the resonance, the reactance of the inductor and the reactance of the capacitor cancel each other, resulting in the input impedance being the maximum set in equal R. As shown in the figure, the resonance frequency is given by this equation. As in the case of series RLC circuit, clearly the voltage reached the maximum at this frequency assuming a constant current source. Resonance response and bandwidth. It can be shown that a parallel RLC circuit behavior near the resonance frequency is similar to that of a series RLC circuit. Consider the behavior of the input admittance of a parallel resonance circuit near resonance frequency. let omega equal omega r plus delta omega, where the omega r is small. So in this equation, where the Qr is the Q factor at the resonance frequency, and the slope of susceptance near the resonance frequency is 4 pi c, while the slope in the high frequency length is 2 pi c. Now consider the bandwidth when the frequency is such that y in square equal to 2g square. The power delivered to the circuit is 1/2 that at the resonant frequency. If Bw is equal Fu minus Fi is the bandwidth, then delta omega is equal to 2 pi multiplied by Fu minus Fr, so it's equal to the 2 pi Bw over 2 at the upper band 8. Thus that in this equation you will see the hand of the Bw is equal to the Fr over Qr. Multiple resonance. The multiple resonance is desirable when a device operates in various frequency bands. For example, consider the circuit in the figure. The impedance of the circuit is given by this equation. If we plot the reactance to resonance frequency, can be observed the frequency at which the reactance is zero is called the zero frequency, while the frequency at which the reactance is infinity is called the pole frequency. Two resonance frequencies are given by this equation. Therefore, the impedance can be rewritten as this equation, where the Fr1 is the zero frequency, the Fr2 is a pole frequency. Now consider the circuit in the figure. The admittance of the circuit is given by this equation. Thus the impedance can be written in the form of this equation. And observe the two forms of the impedance equation. One can conclude the general form of a lossless multiple resonant circuit impedance equation as follows in this equation, and where the x is either omega or 1 over omega and h is equal as constants. The next one is a network function. To analyze more complicated network, it is more convenient to use the Laplace transform. We follow that the impedance is expressed in transform domain for the one-port network. The input impedance can be given by the following function: driving point impedance function, driving point admittance function. For the two-port network, for transfer function are defined as the follow in this voltage transfer function, current transfer function, transfer admittance function, and the last one is transfer impedance function. Foster reactance theorem. Foster reactance theorem is an important theorem in the field of electrical network analysis and synthesis. The theorem states that the reactance of a passive lossless two-terminal one-port network always strictly monotonally increases with frequency. It is easily seen that the reactance of inductor and capacitor immediately increase with the frequency, and from that basis of proof for the passive lossless network generally can be constructed. Explanation of the Foster reactance theorem. Reactance is the imaginary part of the complex electrical impedance. Both capacitor and inductor possess reactance and are frequency dependent. The specification that the network must be passive and lossless implies that there are no resistor or amplifier or energy source in the network. The network consequently must consist entirely of inductor and capacitor, and the impedance will be purely an imaginary number with zero real part. Foster theorem applies equally to the admittance of a network. There is the susceptance of a passive lossless one-port monotonally increase with frequency. This result may seem counterintuitive, since admittance is the reciprocal of the impedance, but it easily proved if the impedance is in this equation Z equal Ix, where X is a reactance and I is the imaginary unit. Then the admittance given by this equation. So where the B is susceptance, if the X is monotonically increase with frequency, then 1 over x must be monotonically decreased. Minus 1 over x must be consequently be monotonically increasing, and hence it is proof that b is increased also. It is often the case of network theory that the principle of precedence apply equally well to the impedance or admittance. And the last content in this topic is about the ladder form. Recall the ladder network previously shown using the previous result with zk equal ak multiplied by s and yk equal bk multiplied by s. The driving point impedance function is then given by this equation as s equal to j omega. Obviously, zk represents the reactance of a coil of inductance, ak and yk the susceptance of a capacitor of capacitance, bk. If we assign Lk equal to Ak and Ck equal to Bk, we get the ladder network shown in the figure, which is the realization of the ladder form for Zs. A study of this network revealed that Z possesses poles both at the origin and infinity. Zs will have a zero at the origin when Cm is short circuit, and the Cs will have a zero at the infinity when L1 is short circuit, and the impedance function will have zero both at the origin and at infinity when both L1 and Cm are eliminated by shorting circuit. An alternative ladder represent is obtained by writing the polynomial in the Zs in ascending power of s in this equation, and we carrying out the process of division and inversion, we can write the equation by this. The network corresponding to this continuous fraction is shown in the figure. This form is called the ladder second form of the driving point impedance. And the next topic is a two-port network. In general, it's easy to analyze any electrical network if it's represented with an equivalent model, which gives the relation between input and output variable. For this, we can use two-port network representation. As the name suggests, two-port network contains two ports, among which one port is used as an input port and the other is used as an output port. The first and second port are called as port 1 and port 2 respectively. One-port network is a two-terminal electrical network in which current enters through the one terminal and leaves through another terminal. Resistor, inductor, and capacitor are the example of one-port network because each one has a two terminal. One-port network is representation in this figure. Here, the pair of terminal 1 and 1 represent a port. In this case, we having only one port since it's a one-port network. Similarly, two-port network is a pair of two-terminal electrical network in which current enters through one terminal and leaves through another terminal of each port. Two-port network representation in this figure. And here, one pair of the terminal 1 and 1 represent one port, which is called as port 1, and the other pair of terminal 2 and 2 represent another port, which is called as port 2. There are four variables V1, V2, I1, and I2 in a two-port network as shown in the figure, out of which we can choose two variables as independent and another two variables as dependent. So we will get six possible pair of equations. This equation represents the dependent variable in terms of independent variable. The coefficients of the independent variable are called as parameters. So each pair of the equation will give a set of four parameters. Two-port network parameter. The parameter of a two-port network are called as two-port network parameter, or simplified to port parameter following the type of two-port network parameter that consists of Z parameter, Y parameter, T parameter, T dat parameter, H parameter, and G parameter. In set parameter, we will get the following set of two equations by consider the variable v1 and v2 as dependent and i1 and i2 is independent. The coefficient of the independent variable i1 and i2 are called as set parameter. So you will see in this equation. And the set parameter are all of this equation. So the set parameter are called as an impedance parameter because this simplifies the ratio of voltage and current unit of C parameter are ohms. We can calculate two set parameter to set 1 and set 2 by doing open circuit of port 2. Similarly, we can calculate the other two set parameter set 1 and set 2 by doing open circuit of a port 1. Hence, the set parameter can also set as an open circuit independence parameter. And we got an example of the set parameter referenced by NASO Academy, so you will see in this video how to solve the set parameter.
So according to the problem, we are required to find the Z parameters of the below given two-port network. So this is the two-port network given in the problem and we are required to find the Z parameters. This means we need to find the Z parameter matrix, which is a 2 by 2 matrix having the elements Z11, Z12, Z21 and Z22. So we need to find the 4 elements of the Z parameter matrix, and there are 2 steps required to calculate the Z parameters. In step number 1, we will assign the currents in all the branches of the network. So let us assign the currents in all the branches. I1 is the current in this branch, I2 is the current in this branch, and at this node, applying KCL, we will have I1 plus I2 as the current in this branch, and V1 is the voltage between these two terminals, and V2 is the voltage between these two terminals. In step number 2, we will develop the input KVL equation and the output KVL equation. So let us develop the input KVL equation. We will have plus V1, then we have minus 2I1, minus 2I1. After this, we have minus 4I1 plus I2, minus 4I1 plus I2 equal to 0. From here, we will have V1 equal to 6I1 plus 4I2. Let's say this is equation number 1. So we are done with the input KVL equation, and now we will develop the output KVL equation. We will have plus V2 minus 6I2. After this, we have minus 4I1 plus I2, minus 4I1 plus I2 equal to 0. From here, we will have V2 equal to 10I2 plus 4I1, and I will write 4I1 first and then I will write plus 10I2. Let's say this is equation number 2. Now if you remember the previous lecture, I told you to note down two equations. The first equation was V1 equal to Z11 I1 plus Z12 I2, and the second equation was V2 equal to Z21 I1 plus Z22 I2. Now when you compare equation number 1 with this equation, you will find Z11 is equal to 6, Z12 is equal to 4. So we can say that the impedance matrix will have the first element equal to 6 and the second element equal to 4. And after this, when you compare the equation number 2 with this equation, you will find Z21 is equal to 4 and Z22 is equal to 10. So the second row will have the elements 4, 10. So this is our answer. So I hope the solution and the steps required to solve the question is clear to you.
So the next parameter is a Y parameter. So the Y parameter is also known as admittance parameter or short circuit parameter. Are the properties used in electrical engineering to describe the electrical behavior of linear electrical network. These Y parameters are used in Y metric, admittance metric, to calculate the incoming or outgoing voltage and current of a network. So Y parameters are also known as short circuit impedance parameter. They are calculated under open circuit condition, that is to say that Ix equal to infinity, where the x1 and 2 refer to the input and output current flowing through the port of a two network. So the Y parameter are commonly used alongside by the Z parameter, H parameter, and ABC parameter to model and analyze the transmission line. So in this video, we'll show you how to solve the Y parameter by its reference by the NASO Academy.
So this is our two-port network, and you can see that we have only resistors in this network, and therefore we are calling the network resistive two-port network, and we are required to find Y11, Y12, Y21 and Y22. These are the four elements of the admittance matrix, and we are required to find all four of them. And in order to find these four parameters, we will first find the four impedance parameters Z11, Z12, Z21 and Z22, because we know that the inverse of the impedance matrix will be equal to the admittance matrix, and I have already explained how we can calculate Z11, Z12, Z21 and Z22. So pause the video and try to solve the question on your own. I hope you tried solving the question, and now I will provide you the solution. We will first calculate the Z parameters, and we very well know that in order to calculate the Z parameters, the step number 1 is to assign the currents in all the branches of the two-port network. Current I1 is entering this node and it is getting divided into two currents. Let's say current in this branch is equal to I1 prime and current in this branch is equal to I1 double prime. Now focus on this node. You will find current I2 is entering the node and current I1 double prime is also entering the node, and therefore according to KCL the leaving current will be equal to I1 double prime plus I2. Now focus on this node. I1 prime is the entering current, I1 double prime plus I2 is also the entering current. Therefore, the leaving current according to KCL will be equal to I1 prime plus I1 double prime plus I2. And from here we can see that I1 prime plus I1 double prime is equal to I1. So in place of I1 prime plus I1 double prime, we can write I1. So current in this branch is equal to I1 plus I2. Now let's move on to the step number 2, in which we will obtain the input KVL equation and the output KVL equation. The input KVL equation will be plus V1 minus 10 multiplied to I1 prime minus 40 multiplied to I1 plus I2. We have plus V1 minus 10 multiplied to I1 prime minus 40 multiplied to I1 plus I2 equal to 0. From here we will have V1 equal to 40 I1 plus 40 I2 plus 10 I1 prime. And when you compare this equation with the standard equation in case of Z parameters, you will find it is not the standard equation. Similarly, when we obtain the output KVL equation, we will find it is also not the standard output KVL equation, and therefore our solution is getting complicated. So till now we have not simplified the problem, but we have complicated it. And I can see that here we have the delta connection, and we can replace this delta connection by the star connection. We will have the connection of 3 resistors like this, and upon conversion you will find we can easily have the standard equations. So let us perform the conversion. Let's say this resistor is resistor R1, this resistor is resistor R2, and this one here is resistor R3. And we know R1 will be equal to 10 multiplied to 20 divided by 10 plus 20 plus 5. So R1 will be equal to 200 divided by 35, and it is equal to 5.7 ohms. And R2 will be equal to 20 multiplied to 5 divided by 35. So R2 is equal to 100 divided by 35, and it is equal to 2.85 ohms. And now we will calculate our third and last resistance, R3. R3 will be equal to 10 multiplied to 5, which is 50 divided by 35, and it is equal to 1.43 ohms. Now when we reconstruct our network, we will replace this connection by this connection, and this resistor is R1, hence its value will be 5.7 ohms. This resistor is R2, therefore its value is 2.85 ohms, and this one here is R3, hence its value is 1.43 ohms. Now you can notice one thing, this resistor and this resistor are connected in series, therefore we can have a single resistor in place of them having the value 41.43 ohms. So we will have a single resistor having the value 41.43 ohms. Now it is very easy to find out the input KVL equation and the output KVL equation. Current in this branch will be I1 plus I2. Now let's apply the KVL in this loop. We will have plus V1 minus 5.7 multiplied to I1 minus 5.7 multiplied to I1, then minus 41.43 multiplied to I1 plus I2 minus 41.43 multiplied to I1 plus I2 equal to 0. From here we will have voltage V1 equal to 47.13 I1 plus 41.43 I2. This is equation number 1. Now we will obtain the output KVL equation, and for this we will apply KVL in this loop. We will have plus V2, then minus 2.85 multiplied to I2, minus 2.85 multiplied to I2, then minus 41.43 multiplied to I1 plus I2, minus 41.43 multiplied to I1 plus I2 equal to 0. From here we will have voltage V2 equal to 41.43 times current I1 plus 44.28 times current I2. This is equation number 2. Now we will compare the first equation with the standard equation V1 equal to Z11 I1 plus Z12 I2. So we are getting Z11 equal to 47.13 and Z12 equal to 41.43. Now we will compare equation number 2 with the standard equation V2 equal to Z21 I1 plus Z22 I2. So we are getting Z21 equal to 41.43 and Z22 equal to 44.28. So in this way we have obtained all the 4 elements of the impedance matrix, and in the previous lecture we saw that the admittance matrix will have the elements in terms of Z parameters as Z22 divided by the determinant of impedance matrix, then we have minus Z12 divided by the determinant, then we have Z21 with negative sign divided by the determinant, and finally we have Z11 divided by the determinant. So we will calculate the determinant of impedance matrix. The determinant will be equal to 47.13 multiplied to 44.28, 47.13 multiplied to 44.28 minus 41.43 multiplied to 41.43. So we have square of 41.43. When you solve it, you will get the determinant is equal to 370.45. So now we can easily have our admittance matrix. In the next step, we will put all the values. The first element will be 44.28 divided by 370.45, 370.45. Then we have minus Z12, which is 41.43 divided by 370.45. After this we have minus Z21 divided by the determinant, and Z21 is equal to 41.43. So we have minus 41.43 divided by 370.45, and then we have Z11 divided by the determinant. Z11 is 47.13. So we have 47.13 divided by 370.45. Now take out your calculator and solve it. I will give you the final answer. The first element will be 0.1195. The second element will be minus 0.1118. This element will be minus 0.1118, and the final one is 0.1272. So in this way we have obtained all the 4 parameters of the admittance matrix, and this is our answer.
The last parameter that we focus on is ABCD parameter. It is also known as a chain or transmission line parameter, a generalized circuit constant used to help model transmission line. More specifically, ABCD parameters are used in the two-port network representation of a transmission line. The circuit of such a two-port network is shown in the figure, and so it's that important for power system engineer to be through with the mathematical modeling of how this power is transmitted by ABCD parameter, and a two-port model is used to simplify this complex calculation. To maintain the accuracy of the mathematically modeled transmission line are classified into three types: short transmission line, medium transmission line, and long transmission line. So this is the example of the ABCD parameter that's referenced by NASO Academy. This will show you how to solve the ABCD parameter.
Alright, now let us understand the solution of this problem, and we will first find out the set of equations we have in case of Z parameters, and we know step number 1 is to assign the currents in all the branches of our two-port network. This is port number 1, the input port, and the voltage between the two terminals will be V1, and current I1 will enter the two-port network. This is port number 2, the output port, and the potential difference between these two terminals is equal to V2. And we know, according to the convention, current I2 will enter the two-port network. Now we know the current in this branch, it is I1, and we want to find out current in this branch, and in this branch. And we can easily have current in this branch because we can see that across 2 ohm resistor the voltage is Vx. Therefore, current through 2 ohm resistor will be Vx divided by 2, and the direction of this current will be top to bottom, because we know in resistor power will get dissipated, and therefore current will enter the positive terminal and it will leave the negative terminal. Now to find out current in this branch, we will apply KCL at this node, and you can see that current I1 is entering the node and current Vx by 2 is leaving the node, and therefore this current leaving the node will be equal to current I1 minus current Vx by 2. Now let us find out current in this branch, and for this we will apply KCL at this node. I1 minus Vx by 2 is entering the node, and I2 is also entering the node. Therefore, this leaving current will be equal to I1 minus Vx by 2 plus current I2. So in this way we have obtained currents in all the branches we are having in our two-port network. Now we will find out the input KVL equation and the output KVL equation. The input KVL equation will be plus V1, then we have minus I1 multiplied to 1 minus current I1 multiplied to 1. After this we have minus Vx equal to 0. So from here we can say that voltage V1 is equal to current I1 plus voltage Vx, and let's say this is our equation number 1. And now let us find out the output KVL equation, and the output KVL equation will be plus V2, then we have minus I1 minus Vx by 2 plus I2 multiplied to 4 minus inside the bracket I1 minus Vx by 2 plus current I2 multiplied to 4. After this we have minus 5Vx equal to 0, and when you simplify this you will have voltage V2 equal to 4 times current I1 plus 4 times current I2 plus 3 times voltage Vx, and let's say this is our equation number 2. Now when you compare equation number 1 and equation number 2 with their standard forms, you will find they are not in standard forms, and therefore we cannot proceed further. And the problem is there because Vx is present in both the equations. So to have the standard equations, we are required to write down Vx in terms of I1 and I2. This means we are required to find relation between I1, I2 and Vx. Now if I connect this point to the ground, then we know that potential at this point will be 0 volt and potential at this point will also be 0 volt, and therefore potential at this point will be Vx and potential at this point will be 5 times Vx, 5 Vx. And now we will apply KVL starting from this point, following this path and ending at this point. We will have Vx, then we have minus I1 minus Vx by 2 multiplied to 6 minus I1 minus Vx divided by 2 multiplied to 6. After this we have minus I1 minus Vx by 2 plus I2 multiplied to 4 minus I1 minus Vx by 2 plus I2 multiplied to 4, and then we will equate with 5 times Vx. We will equate with 5 times Vx. When you simplify this, you will find voltage Vx is equal to 10 times current I1 plus 4 times current I2. And now when you put Vx equal to 10 I1 plus 4 I2 in equation number 1, when you put Vx in equation number 1, you will find voltage V1 is equal to 11 times current I1 plus 4 times current I2, and let's say this is our equation number 3. And now we will do the same thing with equation number 2. We will put Vx in equation number 2, and this will give us voltage V2 equal to 34 times current I1 plus 16 times current I2, and let's say this is our fourth equation. And in this way we have obtained the set of standard equations we have in case of Z parameters, and therefore 11 is our parameter Z11, 4 is our parameter Z12, 34 is our parameter Z21, and 16 is our parameter Z22. And we have already performed the conversion of Z parameters to ABCD parameters, and therefore we know that parameter A is equal to parameter Z11 divided by parameter Z21. Parameter B is equal to the determinant of impedance matrix divided by parameter Z21, and parameter C is equal to 1 over Z21, and the last parameter, parameter D, is equal to Z22 divided by Z21. So from here we can find out all 4 ABCD parameters. But how will you calculate ABCD parameters when you don't remember these conversions in your examination? In that scenario, you will follow the standard procedure, and the standard procedure is to obtain the set of equations we have in case of ABCD parameters using these two equations. And when you compare the second equation we are having in case of ABCD parameters with equation number 4, you will find we have the same set of variables. Therefore, we can have the second equation of ABCD parameters from equation number 4. So we will rearrange equation number 4 and we can write 34 I1 is equal to V2 minus 16I2, or we can write I1 is equal to 1 divided by 34 V2 minus 16 divided by 34 I2. When you compare this equation, let's say equation number 5, with the second equation of ABCD parameters, you will find parameter C is equal to 1 divided by 34. When you solve it, you will have 0.02941, and parameter D is equal to 16 divided by 34. 16 divided by 34, when you solve it, you will have 0.4706.
So the last topic of the midterm of the transmission line is a filter. A filter is a two-port device used to control the frequency response at a certain point in a system by providing transmission at frequency within the passband of the filter and attenuation in its stopband. It can be classified by magnitude response as low-pass filter or LPF, high-pass filter, HPF, band-pass filter, BPF, and band-stop filter, BSF. It has wide range of application, including desired frequency band selection and unwanted band rejection, noise reduction, and the last one is a channel selection in mobile and satellite communication. So how to classification of filter is depending on the type of element used in their construction. Filter are classified into two types. The first one is a passive filter. A passive filter is built with passive components such as resistor, capacitor, and inductor. And the second one is an active filter. An active filter makes use of active elements such as transistor, op-amp, in addition to the resistor and capacitor. So according to the operating frequency range, the filter may be classified as a low-pass filter, band-pass filter, high-pass filter, and band-stop filter. For the low-pass filter only allow low-frequency signal from 0 to its cutoff frequency of FC point to pass while blocking any higher frequency signal. So you will show you in the figure. So and the next one is a band-pass filter. The band-pass filter allows signal falling within a certain frequency band setup between 2 points to pass through while blocking both the lower and higher frequency either side of this frequency band. So it will be easily to understand by you observe the figure. Next one is a high-pass filter. The high-pass filter is only allow high-frequency signal from its cutoff frequency FC point and higher to infinity to pass through the while blocking those any lower. So you will see the high pass is only allow the high frequency to go out the output. And the last one is a band stop filter. The band stop filter blocks signal falling within a certain frequency band setup between 2 points while allowing both the lower and higher frequency either side of these frequency bands. So you will see in the picture that how the stop filter is using. So the last one, use of filter. Filters are widely used in a communication system to separate various voice channels in carrier frequency telephone circuit. And the filters are widely used in a radio and TV. So the last one, the filter is used in the communication, transmitter, receiver, multi-channel communication, and the other. So this is all of my presentation about the transmission line in the midterm. I hope you enjoy watching this video and learn how to learn this subject. Thank you for attention.